guys, this is Professor Janacek, and I want to go over an example where we find extrema and saddle points of a function in several variables. Let's take a look at this example here. We're going to determine all the relative extrema and saddle points for f of xy equal to x to the fourth plus y to the fourth minus 4x minus 32y plus 10. So first off, we need to find the critical points. Remember, the critical points is when the first partials are equal to 0 or the first partials are undefined. So if we take a look at the first partial with respect to x, we end up with 4x cubed minus 4x, and the first partial with respect to y is 4y cubed minus 32. Now, I notice here that these are never undefined, so I don't have to worry about that portion of it. They're never undefined. But I do need to see what happens when they're equal to 0. So we will start by letting 4x cubed minus, oh, that shouldn't be an x on there. That's just a 4. It's a derivative. All right, 4x cubed minus 4 is equal to 0, and 4y cubed minus 32 is also equal to 0. If we solve those, let's see, for x is equal to 1 for the first one, and y is equal to 2 for the second one. Thus, we get the point 1, 2 is our only critical point. All right, now our second derivatives will give us what happens at this point. Will tell us whether we have an extrema or a saddle point. So what we'll need to do is we'll go ahead and find all of the first partial derivatives. Let's go ahead and make a list of those. F sub xx is 12x, and f sub xy, in no particular order, is, so that's the first partial, so we're still looking at this one for both of these. Partial with respect to x is 12x, partial with respect to y, though, that's 0. All right, how about f sub yx. So that's going to be taking a look at this one and taking the derivative with respect to x. Well, that turns out it's also 0. And then f sub yy. That's again looking at this one. The derivative with respect to y gives us 12y squared. Actually, I think I left the square off of that one as well. 12x squared and 12. There we go. Much better. All right, I'm happy with this. Now, what we want for D is the discriminant of the matrix. Remember, I said it's the discriminant here of the matrix formed by this. So I actually put it in that order just so that it'd be easy to transfer into a matrix. And if you remember how to find, notice I'm using those vertical lines to identify it's the discriminant of this matrix. Remember the way we found the discriminant is we would go along the diagonals and take the difference of those. It's always the top left to bottom right. Multiply those, and then subtract off the top right multiplied with the bottom left. So in this case, that gives us, you could also take a look at it in terms of the formula that we have written up here. It's the first partial, it's f sub xx times f sub yy minus f sub xy squared. You could also write it that way. Either way, you end up with the same thing. So that's 12x squared times 12y squared minus 0 squared. So we end up with 144x squared y squared. So now what we need to do is we're going to go through all of this mess here. We need to evaluate this at our critical point. Our critical point is 1, 2. If we evaluate this discriminant at 1, 2, we get what would that be? 576, which is definitely greater than 0, so it's either this first case or this second case. Now we just have to see what happens for f sub xx evaluated at that critical point. So f sub xx evaluated at 1, 2 looks like it's 12, which is also greater than 0. All right, I think that tells us what we need. The discriminant is greater than 0. F sub xx is greater than 0. Must be a relative minimum. And there you go. Enjoy.